Good morning, students. Welcome to the lecture series. My name is Pooja, and today we are going to discuss about the microactuators. As in Unit 4, we have already discussed about the microsensors. The microactuator is another block diagram of MEMS technology, you can say. First, the signal is being sensed by a sensor, and then that signal, the output of that signal, is being sent to microactuator. Basically, microactuator is a transducer that convert the electrical output in mechanical output. The sensor is used to sense any environmental activity into electrical signal, and that electrical signal is being sent to the microactuator, and that microactuator converts this form of energy into mechanical output. MEMS actuator. Basically, we will discuss about the thermal actuator and electrostatic actuation. So, two types of processor will be discussed in the MEMS actuators. So, electrostatic actuation is the actuation which is produced by the electric field by the capacitor. So, there are two basic configuration of the capacitor that can be used, like the parallel plate or a interdigitalized comb capacitor. These are this is the digitalized comb capacitor and parallel plate capacitor. So the what are the difference between these two types of integration, these two types of configuration? So first, the interdigitalized comb capacitor, it has the fringes electric field, you can say. These are the fringes electric field, and within the parallel plate capacitor there is a direct field between the plates. As you can see, the interdigitalized comb capacitor have parallel plates, have direct field also. So we can say that in terms of configuration, when we talk about the parallel plate capacitor, it has direct field between the plates, and in interdigitalized comb capacitor there is fringed field as well as direct field. So this is all about discussing this statement. Next, now some mechanical or numeric terms are being discussed, like in parallel plate capacitor, the capacitor of fixed parallel plate capacitor, which is shown in this equation, and the parameters are constant, like capacitor C equals to epsilon A over G. It means epsilon is the permittivity of any material that is of plate, and A is the area, and G is the gap between the plates. This is the formula when the distance, the gap between these two plates is fixed. When the gap between these two plates are movable, like the Z, if the gap between the plates are movable, then this gap G will be G minus Z. Okay, so as we have seen, the gap is discussed by the Z, to G minus Z. So for variable parallel plate capacitor, C equals to epsilon A over G minus Z. Okay, this is about the capacitance. And now if we discuss about the energy, the W, now with respect to the voltage across the plate, as there is a voltage induced in between the plates, so there will be some work done, there will be some energy. So that energy W can be defined by the formula half epsilon A over G minus Z into V square, that is a voltage across them. So next, if we talk about the potential energy, so electrostatic force is also acting on the plate. So this is an important parameter. So on differentiating this work, this energy, we can produce the electrostatic force F. So on differentiating this energy dW with respect to the dz gap, that is being defined by the force, electrostatic force F, it can be half epsilon A G minus Z square into V square. This is the potential energy, you can say, in terms of Lagrange's equation also. If you are being asked for the Lagrange's equation, you can derive this. So how can you derive this? On differentiating the work done by the capacitor, we can get the potential energy, we can get the electrostatic force, that is F equals to half epsilon A G minus Z square into V square. So this is all about the parallel plate capacitor. And if we talk about the interdigitalized comb capacitor, so you have seen this schematic, this configuration. There are two fixed plate are there and one plate is movable. This third one and the produced EMF voltage is between this fixed plate and this movable plate. Okay. Now what are another things we should be in our mind, that the interdigitalized comb capacitor configuration is shown as it has movable plate inserted between two fixed plate. The direct parallel plate electrostatic force and the fringed field force are the two types of electrostatic forces which are acting. We have already seen there are fringed and there are parallel. The motion of movable plate, yes, this is the main parameter, how the plate is moving. Like this is the plate, this cannot be moved like this because this gap should be maintained between these two plates. This gap should be equal, so this cannot be moved like this. So this plate will be moved from upward to the downward direction. Okay. Now the motion of movable plate, the motion can only be in the direction that insert the movable plate between two fixed plate and maintains the gap between them. So to maintain the gap between them, only upward to the downward direction is there. So the plate will be moved like upward to the downward direction. Now with this interdigitalized comb capacitor, if the combs, or you can say if the plate's width is W, then the capacitor can be defined as 2 epsilon W L minus X over G. And with this we can find out the F, or you can say we can find out the electromotive force, that is epsilon W over G into V square. This is all about the interdigitalized comb capacitor. So we have discussed about the electrostatic actuation, which is being produced by producing an electric field by the capacitor. Now we will discuss about the thermal actuation. Basically thermal actuation is means by providing any heat, by providing any thermal expansion of solid material, we can actuate it. Okay, like thermal actuation uses thermal expansion of material. Like we have already discussed about what is the formula for the thermal actuation. Thermal expansion we have already discussed in our last lecture. Epsilon equals to epsilon alpha T into del T. What it defines? It defines that the mechanical strain, epsilon is the term that is used for defining the strain. The strain, mechanical strain, is proportional to the change in temperature, and if the proportionality sign will neglect, then epsilon equals to alpha T into del T. And alpha T, what is alpha T? Alpha T is the proportionality constant that is known as thermal expansion, the coefficient of thermal expansion. Okay. So to achieve mechanical actuation, this formula is very useful. The thermal expansion of solid material is characterized by coefficient of thermal expansion, that is alpha T. Okay, so this is all about the thermal expansion. So in thermal actuation, thermal expansion is the main parameter, and in electrostatic actuation, electric field is the main parameter. So this is all about today's PPT. Next, we have already discussed about micro actuation and micro sensors. Next we will go to the fabrication procedure of the MEMS devices. So